So I'm going to talk to you about work that I've done with Ben Sleater, Leonardo, and a fourth colleague, my supervisor at University of Toronto, this is part of my thesis work, looking at a model of carbon and land use change in Hawaii. Okay, and this is actually a model that was used as the case study for a couple papers we published on the methods behind state and transition simulation models and the stock flow addition to that we talked about in the advanced course. Okay, so the model is actually pretty simple, but I think it provides a reasonable starting point as an example of the kinds of things you can do with stocks and flows. So the model this case study is based in Hawaii, and we're looking at projecting, firstly, land use, land cover change out into the future for the state of Hawaii. The STSM that we produced for this example, we had 7 classes, so it's actually a fairly simple model, but this is sort of a standard way that we find people use the approach for doing land use, land cover change, using classes that line up with remotely sensed data on land use, land cover change. And we actually introduced as well, used the strata feature to incorporate moisture zones and differences in dynamics across 3 different moisture zones. This is actually a fairly small model in sort of spatial extent. We ran it at 1 kilometer resolution with about 16,000 cells, and we ran it forward 50 years with an annual time step. And we only looked at 2 scenarios. Again, the purpose of this was to demonstrate the approach, so we kept the simulations very simple. It wasn't intended to actually make real projections of land use land cover change. It's more to demonstrate the features of the approach. And we ran 100 Monte Carlo realizations for all our simulations. And so here's an example of, this is a figure of how this land use land cover change model works. You have 7 states, as I said. You have a number of different transitions, and again, they're fairly simple. We have agricultural expansion, contraction, where we're moving land back and forth between the agricultural state into other states. We have urbanization, where we're turning different chunks of land into developed. We modeled wildfire in here in some of the vegetative states. We had this one dynamic that was going on in Hawaii, which was the encroachment of shrubs into grasslands that we modeled. And we also had the harvest of eucalyptus plantations. So to relate these to the features in the software, we had transition targets set for some of the transitions, and others were modeled by probabilities. And that was really based on what kind of data we had to parameterize the models, the transitions. So parameterizing, first the transitions that were parameterized using targets. 2 of the features that we used were obviously transition targets, and we also used the distribution feature that we talked about in the advanced course, where we set those targets and incorporated some uncertainty into our level of transitions over our simulation. This time we had very little data on it, but we sampled for using a uniform distribution between the min and the max area that we observed transitioned over historical period using some historical data on this kind of stuff. We also, for some of the transitions, we constrained where they could occur spatially using the spatial multiplier feature. And so we had maps, this kind of map where we had a zoning map for the state. And so we knew where different, which different activities could take place. So for example, urbanization, we knew that it couldn't happen in conservation areas, areas zoned as conservation. It might happen in agricultural areas, and it was most likely to occur nearby to urban or rural areas, okay? So we could actually modify the probabilities so that it was actually twice as likely to happen in and around existing urban areas as it was into agricultural. Then we used the adjacency multiplier feature that we just touched on briefly in the course, advanced course, where we were able to model that, in this case, we're looking at urbanization, the probability of urbanization and occurring, and we made it a function of how close a cell was to other existing developed cells. So this created a dynamic where the urbanization spread out from the existing urban areas with increased probability based on how many other neighboring cells were also already in the developed state. For the transitions that were modeled as probabilities, we had plantation harvest that we just modeled probabilistically because we had very little data on it. We didn't have targets for it. We modeled shrub encroachment also using probabilities. And the wildfire, which is the more interesting one, was modeled very much the way we described it in the advanced course yesterday, where we were making the wildfire probabilities match the historical record of area burned and fire size distribution. Again, using transition, well, there are several features there, but for the wildfire, for example, we used temporal transition multipliers, sampling from distributions and external variables to drive those. Okay. This is some of the results how we chose to present the results, just something a little different from some other work. So this is, how do I use the, it's not that button.
The red button. The
red button, yeah. So this is how we just chose to display projections for transitions first, okay? And it's always a challenge to find a way to visualize uncertainty in your projections. We're always trying to work on that. So this is what we came up with for this example. So here's a map of the existing land use cover change. We're just looking at the island of Hawaii, the Big Island, in 2011. So you get some idea of, for reference, where you are in the island. And here we're looking at the annual transition probability, the mean for that over the 100 Monte Carlo simulations, right? So and also averaged over all 50 years. So this is just the grand total average probability of each cell transitioning occurring a transition of one of these 5 different transition types. So for example, in urbanization, you can see there's a higher probability of transitions occurring in and around existing urban areas. Same kind of thing for agricultural expansion, and you see some idea of where it's most likely that wildfire occur out into the future, okay? For projecting states or displaying states now, this is always an even bigger challenge we find to visualize this stuff. And so here what we've done is we've shown one Monte Carlo of what the projection might be for the future state of the Big Island. So it's just one Monte Carlo, but that doesn't convey any of the uncertainty, right? So again, the approach we used here to try and characterize and display that uncertainty is to show a map for each one of our possible future states. I just show 4 of them here, what the probability is of each cell being in that state out at the end of the simulation 2061. So for example, here you can see there's a probability of 1 that you'll still be in a developed state 50 years later if you're already in things never transition out of developed states. And the probability sort of goes down as you get further away from existing urban areas. And you get similar patterns for the other transition state or for the other states. So that's the land use change side of the model. Now I'm just going to talk a little bit about the stock flow model we added to track terrestrial carbon. So the question here was, can we add terrestrial carbon to an existing land use land cover change model? And what the intent here of doing it in STSM, what we wanted to try and do is see if we could integrate the projections of land use change with carbon, which is a fairly novel thing to do, and also propagate those uncertainties that you saw in land use change through into uncertainties about future projections of carbon. And of course, as we talked about in the course yesterday, because of the challenges modeling soil dynamics, using the attribute feature really isn't quite enough. If we want to do a good job of soil with the lag dynamics, we really want to use something like the stock flow approach. Okay, so this is the stock flow model quickly that we developed for this project. And here we had 4 major stocks that we were tracking, stocks of carbon, pools of carbon, 2 others that were included just to create a mass balance of our carbon in our model, okay? And we had a number of flows. The first was the growth of living biomass, where carbon moves from the atmosphere into living biomass. We had several other flows to then move that carbon around over time within the different pools, and then a set of flows that moved carbon over time again off into back to the atmosphere due to emissions. And then we had a flow where we allowed some of the living biomass to be transitioned into harvest products. That was both for timber and for agricultural products due to the harvesting of the living biomass. So those are all the sort of automatic flows that we talked about in the advanced course that happen sort of every year, just as time unfolds. We also had some flows that were linked to transitions. So if we look at our state and transition pathway diagram, some of the flows could be triggered by fire in this example. So when a fire occurs, there's movement of carbon between pools. Other flows could occur in response to, say, urbanization. Again, you can, you clear the land, you get emissions from that. You might take some of the carbon and actually harvest it off that land just as you're clearing it, and so on and so forth. So we had transitions that were linked to flows linked to transitions as well. And then we had to parameterize the rates of those flows somehow. And our approach for doing that was to take a biogeochemical model called IBIS, and we ran it under a whole bunch of different scenarios, combinations of different starting conditions, what state you were in, what moisture zone you're in, and we ran it out and created these projected carbon curves of how much carbon you would have in each pool as a function of age. We started our simulations using bare ground and would grow these sort of virtual stands, or in some cases this is forest, but we did it also for grassland and shrubland. We'd grow that land up and see how the carbon moved around according to that model's projections, or as a function of age, okay? And then we converted those that output into flow rates in our stock flow model. We also had to come up with rates of change in carbon, the movement of carbon in response to some of those transitions into, urbanization, wildfire, that kind of thing. And for that, we just turned to IPCC default values for rates of carbon flux in response to different transitions. And the last thing we did is we introduced spatial and temporal variability in the fluxes that occurred in our model. And we did that using flow multipliers, both spatial and non. We didn't talk about that a lot in the course, but it's very similar to the transition multipliers. So we're able to incorporate a variability that reflected differences in productivity across the landscape. So we were able to do that using existing maps off of MODIS data that gave an indication of the MPP in each spatial cell in our simulations. And we also used a Sergo map of soil carbon, and we used that to calibrate the relative amount of carbon that the model started with in each cell in our simulation. The projections for that side of the model, this is how, again, we chose to display them in this study. So here we show, for example, the change in carbon over the full simulation period in two of the pools, the two major pools. So this is sort of an indication, again, over the 100 Monte Carlos of the mean projected change in carbon in two of the pools. And to get a handle on the uncertainty, then we chose to express it this way, where we show the actual width of the 95% confidence interval projected for each cell. So essentially what you're getting here is the darker areas are the areas that have more uncertainty in our projection of change in living biomass, for example, and a change in carbon. And you look, the scales are different. So there's quite a bit more uncertainty in change in living biomass than there is in soil in this kind of example. Okay, and then finally, we can sort of summarize our projections of carbon in response to land use change out into the future into time series graphs. This one up here is sort of showing the net rate of ecosystem accumulation, the net biome productivity under two different scenarios, the blue being if we go out into the future with all of these land use change projections, and then just as a comparison, the red shows what we might project if we only had wildfire. So you can see the net effect of the land use change going out into the future is projected on carbon. So we get projections like that. And we also show here the sort of total carbon that is in the atmosphere pool as a function of time. So just to summarize then, the purpose of this work was just to try and demonstrate this new stock flow method. This was our first attempt to really do it. And so we believe we've sort of developed an approach that's suitable for tracking continuous variables in a STSM. The approach, some of the major features of it is that I think it's relatively intuitive. The stock flow model approach is widely used in business and finance for doing modeling, and I think it's a fairly easy thing to understand, much like state and transitions are. So it's intuitive. It is sort of, you can see it has a lot of parallels with our existing state and transition approach. So it's spatially explicit, it's stochastic, that kind of thing, and it combines the dynamics of both discrete and continuous variables, which up until now we haven't been able to handle continuous variables well as state variables in our models. Some of the limitations yet of the approach is it's still difficult to parameterize these models. There's a lot of parameters, and because they're stochastic and they track uncertainties, it forces you then to try and estimate uncertainties in all your parameters rather than means. And that's always a challenge. It's often challenging enough to come up with means for parameters, let alone distributions for them. And the other is that we haven't used it a lot yet. It's been used for carbon, the sort of stock flow approach. It could be used, as we talked in the course, for other things, but we really haven't tested it much yet. There's only 2 or 3 examples of applications to this approach to date. So that's the end of my talk.